All right, so if you've noticed already, graphs have not gone away. They will not go away until we get to chapter 9. Okay, so we're going to be doing graphs for this chapter, chapter 7, and chapter 8. Okay, but now instead of talking about Euler, we're switching to Hamilton. Okay, so your difference between Euler and Hamilton. Euler says every edge is used exactly once. So, must touch every vertex. And every edge. So, Euler says I have to touch every place and every road to get there. Hamilton came through and said, all right, I like that idea. However, I want to go to my vertex once and only once. Okay, so Hamilton's kind of made it a little bit easier. Not every edge is used. Okay, so we are no longer required to travel every edge. However, it's still, once you've traveled it, you can't travel it again. So I guess we should put here, but once traveled, can't go back. Okay. The only thing that sucks about Hamilton, Euler had a really nice way to figure out if I had a path or a circuit. You could count the degrees and decide whether there was a path or a circuit. Hamilton doesn't have anything easy like that. Okay, so it's just about you trying to guess and figure out what you can do. So if we take a look at graph 1, okay, let's go back over Euler. So if you look at graph 1, is this an Euler circuit, path, or neither? And what tells us that?
It's neither. Want to take it back?
I'd take that back.
It's a circuit.
This one should be a circuit. If you count your degrees, A has 2, B has 4, C has 4, D has 4, E has 4, F has 4, G has 4. So this should be an Euler circuit. Now we need to decide if it's a Hamilton path or circuit. Okay. Again, Hamilton just says, can I start somewhere, visit every dot, and make its way back?
No, it can't make its way back. But it can touch every thingy.
Okay. So you're saying that there's a Hamilton path, but you're saying there's no circuit. Do we all agree?
Yeah.
I'm going to disagree.
Yeah, I'm going to disagree on that.
So remember, Hamilton says I don't have to touch every line. I just have to go to every place. I can easily go around the outside, cut in the middle, and back around. So, yes, there is a path, and yes, there is a circuit. I could have stopped at B and made it a path. So, if there's a circuit, there's automatically a Hamilton path. Take a look at graph number 2. Go back to Euler. Do I have an Euler path or circuit, or neither?
Path.
Okay. Said path. I agree. Here's your odd. Here's your other odd. Everything else is even. Do I have a Hamilton path or circuit?
No. I mean, yes.
I say yes for that.
Okay, you say yes for path. What about a circuit? Remember, you can't cross a line more than once. There's no circuit here. Okay, so I can leave E and I can touch every dot, but Hamilton says once I've gone someplace, I don't want to go back there. So I can't go back to D and make my way back to E. So there is no Hamilton circuit here, but there is a path. What about graph 3? Euler. Do I have an Euler circuit, path, or neither? I heard neither. Why? There's 4 odds. A, B, D, and E all have a degree of 3, which makes this neither for Euler. However, do I have a Hamilton circuit or path? Can I touch every dot and make its way back home?
Yeah.
Yes. I can leave A. There's a whole bunch of different ways to do this. So yes, there's a circuit, and if there's a circuit, there's automatically a Hamilton path. Again, you would just stop a dot early to make it a Hamilton path instead of a circuit. Graph number 4. Euler, circuit, path, or neither? Okay, you said circuit. I agree, they're all even. This is an Euler circuit. What about Hamilton? It's just a path. Perfect. Graph number 5. Euler, circuit, path, or neither? You said neither? This one should be an Euler path. Everything's even except for D and A. Okay. Everything's even except for D and A. What about Hamilton? Do I have a circuit, path? You said just a path. Do we agree with Kimberly? Don't let her dictate your life.
No, wait, no. It's neither.
It's going to be neither. Okay. No matter which way I go, I get stuck. Okay. Once I get C, I can't get anywhere else. Or once I got to F, I can't get anywhere else. So this is no Hamilton path, nor a Hamilton circuit. And what about graph number 6, the last one? Euler, circuit or path first?
Neither.
This should also be neither.
Really?
Yes. Take a look at your odds. A's an odd, B's an odd, E's an odd, D's an odd. Okay. You have 4 odds here, which makes this neither for Euler. Do I have a Hamilton circuit or path?
You have a path.
You got a path, but you don't have a circuit. I agree. I can touch every dot. Perfect. Okay. Questions on identifying Hamilton paths or circuits? Okay, let's find some then. So, helpful hints. Vertices of degree of 1 or 2 are very helpful because they represent required edges that have to be used to reach that vertex. Oh, we skipped the one at the bottom of the last page. Do you notice a relationship between the graph having an Euler path, having an Euler or Hamilton circuit or path? Is there some kind of relationship that's happening here? There's not. Okay. So just because it has an Euler circuit does not mean that it's going to have an Euler path or a Hamilton path and circuit. Okay, just because it has an Euler path does not mean that it's going to have a Hamilton path or circuit. Okay, there is no relation there. Okay, so what we want to do with this is you need to be able to come up with distinct Hamilton circuits. Okay, so we're going to come up with different ways that I can start at A and I can get back to A that is different than any other way we've tried. So here's your first one. I can start at A, I can travel to B, travel to C, travel to D, and go back to A. Can you find me another way to leave A and get back there?
Yeah.
Okay, you said AC. Did you say DB or BD?
I said BD.
All right, well, we're going to go with D because I already have it drawn. So, AC, DB, and back to A. Is there another way? CA. AB, D, C, A. What do you notice about these two? It's reverse order, but these are still distinct. You just went backwards. Okay, so that one works. What else we got?
A, B, D, C.
A, B, D, C. We just did A, B, D, C.
Got it. A, C, B, D, A.
A, C, D, B, A.
I said
We did that.
B,
Huh?
A. B, D, A. Like A to
A,
C to B.
B to D to A. Sorry, I hate doing B, D because it's A, C, B, D, A. Okay? A, C, B, D, A.
And you even wrote it wrong. You have another one.
Where's that?
A, D, C, B, A.
A, D,
C, B, A.
A, D, C, B, A. This one's reverse order. There's one more. What'd you say? A, D, B, C, A. This reverse order. A, D, B, C, A. And these two are reverse. Whoops. I can spell today. Goodness gracious. Okay. So, reverse order is also distinct. There are 6 distinct circuits in this picture. Each way is a different way to start at A and get back there. Okay, when you're trying to list distinct Hamilton circuits, you always want to start at the same letter. Because you can also have a shift circuit. Okay, so what a shift circuit or same circuit means is I've taken what I originally have, and instead of starting at A, I started it somewhere else. But I'm still going in that same order. So, in other words, I can take this one, and instead of starting at A, I can start at D. And then I can go to B, I can go to A, I can go to C, and I can go back to D. Well, that's the same as what you just wrote. It's just starting at a different letter. I can rewrite all of these to start at D. So this one can go DC, AB, D. I can rewrite this one to start at D. DA, CB, D. And these are called shift or same Hamilton circuits because it still goes in the same order that you originally had. You just have a different starting spot. So, in other words, instead of starting at home, you started your trip at Walmart. Instead of starting at Walmart, you started at Burger King. Okay. So, all you did was change where you start. Questions? We got 4 more examples, and we are finished for today. Bless you. Bless you again. Okay. So, example 1. List all possible Hamilton circuits starting at vertex A. It even tells you we have 8 total. When you can't, so we're going to end up with a formula later that talks about complete graphs, and you'll be able to know how many circuits there are. But if there's one like this, they'll tell you, okay? Because this isn't a complete graph. We'll talk about that a little bit later. Okay. Remember, when there's 8 distinct, the reverse is also 1. So once you find a circuit, you can reverse it, and that automatically gives you 2 distinct circuits. So somebody give me one.
Wait, so basically it has to be even, right? It has to be.
You have to touch every dot and make its way back home.
No, I'm saying for like, since it has to have 2 pairs basically, because it's reversed. It has to be.
It's going to be an even amount of distinct circuits, absolutely.
Ready?
Every time. Who's got one?
A, B,
A, B,
C,
C,
D,
D,
E,
E,
F,
F,
G,
G,
A.
A. Look, I can follow the alphabet. A, B, C, D, E, F, G, and back to A. Okay? Remember, now that I've got 1, I technically have 2. I can reverse this. A, G, F, E, D, C, B, A. Okay, that's the only nice part about Hamilton. Okay, so we've got 2. Can somebody find me another one?
Can we do A, F, C, D, E? Or do, oh wait, we
You have to touch every dot. Yeah. Hamilton says you have to go to every place.
A, G, B, E, D,
H,
E,
D,
C, F.
okay. So A, G, B, E, D, C, F, and back to A. Now we can reverse it. A, F, C, D, E, B, G, and back to A.
A, G, F, E, D, C, D, A.
I already have that one.
Oh, you did?
That's the reverse one of that Naiwan gave us to begin with.
Now that kind of got all right. A, F, G, B, E, D, C. Never mind. That doesn't work.
Oh yeah, because you can't get back to A.
harder than I thought it was gonna be.
Not quite as easy as we had thought, right?
A, B, E. Good.
Go ahead, Troy. A, G, B, C. Yes. A, G, B, C, D, E, F, A. F, E, D, C, B, G, A. Woo! That took a minute. You think you got the last one? Oh, he thinks he got skills. Let's see what he's got.
A, B, E, D, C, F, E, A.
A, B, E.
No, it's not up there.
Awesome. A, B, E, D, C, F, G, and back to A. And then, of course, the reverse. So A, G, F, C, D, E, B, and A.
So you do one of these quizzes. You guys do all of it.
How many are like these are these?
I think there's, I don't even think I give you, oh no, there's one. There's one, and it's got six distinct circuits. Yes, there's one,
Oh my God.
and there's six. It's actually the first one on the test. Okay, so if I have 8 distinct circuits that start at A, what about the Hamilton circuits that would start at B or C
They were
or
all
D?
A.
They all have 8. Okay, every last one of them is going to have 8 because again, it's all of these original circuits that you found. We just shifted over to start at a new place. So instead of starting at A, I'd rewrite all these to start at B, and then I could rewrite all these to start at C. My amount of circuits do not change when they're the same. Okay? Let's talk example 2. Find me a Hamiltonian path that begins at A and ends at E. Okay, so Hamiltonian path says I have to stop at every dot. I've got to go to every store. I don't care how you want to think about it. I've got to go to every mailbox, pretend you're a mailman. Okay, I need to start at A and I want to end at E. A, F, B, C, G, D, E. That one works. You could have went A, D, G, C, B, F. No, you couldn't. I lied.
That's all.
Never mind. I tried.
I'm about to say yeah.
You can go A, A, D. Oh, never mind. You can't.
Yeah, because you can't get the F. There's only one way to do that.
Right. I mean, technically, if it didn't start at A, you just do it different.
Technically, yes. But it tells me we have to start at A. Take a look at B. Find a Hamiltonian circuit now that starts at A and ends with the pair of vertices E
It's
to
the
A.
same as the first one. It just has A.
Okay, it's the same as the first one. But now, instead of stopping at place E, I'm going back home. I'm taking that extra trip back home. So again, if I have a circuit, I will always have a path. If there is a circuit there, there will always be a path. You just stop before you go home. You spend the night with your BFF. What about a Hamiltonian path that begins at F and ends at G?
F, A, B,
F, A, D,
B,
Oh, sorry. My bad. B,
E, D, down, I can see that.
C,
Then G.
and G. Okay? F, A, B, E, D, C, and we finish off at G. You got one? F, B, A, E, C, D, G. That one works as well. F, B, A, E, C, G, and D. Or I'm sorry, D, G. My bad. Yeah. Yell at me. I know. F, A.
A, D, D.
I also had F, A, E, B, C, D, and G. I also had F, B, C, E, A, D, G. Okay, so there are several ways to do that one. As long as you can give me one of those, you're good. You don't need to list them all. I just need one. Take a look at example number 3. The following graph has no Hamiltonian circuits or paths. Why not?
You can't,
Once you hit
you
one
can't
point, you can't
hit
go.
every point. Without
Why?
letting go.
What are these lines?
They're bridges.
There's bridges. You have 4 bridges. Okay, you have 4 bridges here. So once you cross that bridge, you can't get back. Because 1, you can't trace that line twice. 2, you can't go back to a place that you've already been. Okay. We've got one more. Find all the Hamilton circuits that start at A. All the Hamilton circuits that start at A.
A, C, F,
A, C, F,
D, E,
D, E,
B, A.
B, A. Don't forget to reverse that. A, B, E, D, F, C, and A. So there's 2. Guess what? We only got 4 more. 2 more, and they're reversed.
A, C.
Hold on. Who got one? What you got? A, E. Oh, I'm sorry. A, D. Okay. E, F, C, B, A. So then we've got A, B, C, F, E, D, and A.
Since it doesn't say distinct, we keep on.
Find all Hamilton circuits, which means you need distinct.
So it would just be the same.
Yes. There's only one more and it's reverse. Can we find it?
A, C, B, A, B, F, D, A.
You got it. A, C, B, E, F, D, and A. Which means I can do A, D, F, E, B, C, A. Okay, so what would I do then for part B if it says find all the Hamiltonian circuits that start at D? What?
And so you gotta go from D to.
Just make all these start at D. Okay, so if they ask you to do something like this, all I do is go up to these ones and start it at D. So D, E, B, A, C, F, and D. Reverse that one. D, F, C, A, B, E, D. You would start this one then at D. So you get D, E, F, C, B, A, D, and reverse it. I'm not going to write the reverse. I think you've gotten that point already. And the last one, I would just do D, A, C, B, E, F, D, and of course, flip it and reverse it. Okay. Whew!
We're done.
Done.